We use it for pretty much everything, right? The light in your room, the phone in your hand, it powers our entire world. But have you ever stopped to wonder what that invisible force flowing through the wires actually is? Well, today we're going to go deep, I mean really deep, inside the wire to find the atomic heart of electricity. So let's just jump right in with the big question. What is electricity, really? Not just the thing that comes out of the wall socket, but what's fundamentally going on? To answer that, we have to start thinking incredibly small. And to get that answer, we have to go back to the very beginning. I mean, the very beginning. Our journey starts inside the atom, the fundamental building block of literally everything in the universe. So, what is an atom? Well, it's the smallest possible piece of anything, really. Think about it. The air you're breathing, the chair you're sitting on, the copper in a wire. It's all just a giant collection of these unbelievably tiny particles. And believe it or not, the secret to all of electricity is hiding right inside this little structure. Okay, let's break this down. Right at the center, you've got the nucleus. That's made of protons, which have a positive charge, and neutrons, which have no charge at all. But orbiting around that center, you see those? Those are the electrons, these tiny particles with a negative charge. And for what we're talking about today, these electrons, they are the absolute stars of the show. But here is where things get really interesting. Not all electrons behave the same way. Their behavior changes a ton depending on what kind of material they're in. And you know what? The freedom of these electrons is the key difference between something like a rubber handle and the metal wire that powers your lights. This right here, this is the whole shebang. On one side, you've got materials where electrons are on a super tight leash, basically locked to their home atom. But on the other side, in metals, you have what we call free electrons. They're barely attached, kind of like little wanderers, free to just hop from one atom to the next without much effort. And this ability, this willingness to let electrons roam around, gives a material a special name, a conductor. Because it has so many of these free electrons, it's like a perfect superhighway, just waiting for them to travel down. And you definitely know these materials. We're talking about things like copper, aluminum, silver, and gold. They are all fantastic conductors. Now, copper is the one you see in wiring all the time, mostly because it's a great conductor, but it's also not crazy expensive. It's the perfect sweet spot. Okay, so we've got these free electrons just hanging out in our metal wire. But so what? They're not doing anything useful yet. How do we get them to do some actual work? Well, that brings us to the whole idea of an electric current. If you look inside a wire that's just sitting there, not connected to anything, those free electrons are just zipping around randomly. It's complete chaos, like a mosh pit. All that movement doesn't actually create any energy we can use. It's just noise. But what happens if we can get all of them to stop bouncing around randomly and start moving in the same direction? Now that is the magic moment. That organized one-way street of electrons is what we call an electric current. It's no longer a chaotic crowd. It's a disciplined march. So let's just lock in that definition. An electric current isn't just about electrons moving. It's about organized movement. It is that steady, continuous, orderly flow of electrons through a conductor. That is what we mean when we talk about electricity flowing. This leads to a pretty obvious question, though, right? Electrons are not just going to line up and start marching on their own. They need a reason. They need a push. And that push has a name: voltage. Honestly, the best way to think about voltage is just as electrical pressure. It's the invisible force that gets all those randomly moving electrons and shoves them, forcing them to start moving in one direction. Without that pressure, without voltage, you get no flow, just chaos. You know, this water analogy makes everything just click. It's perfect. Imagine a wire is just a water pipe. The electrons, that's the water just sitting inside the pipe. So what's voltage? It's the water pressure. If you have zero pressure, the water just sits there, right? But if you crank up the pressure, that water starts to flow, and flow powerfully. It's the perfect way to picture this invisible force. So we have all the pieces now. We have the electrons, the conductor for them to move through, and the voltage to give them a push. Let's put it all together and see how this journey from a single atom translates into powering our entire world. So here it is, the whole sequence from start to finish. First, something like a battery applies voltage, that's our push. Second, that voltage pushes the free electrons in the wire, getting them all moving in an organized line.
Third, that organized flow is the electric current. And finally, that current is what delivers energy to something like a light bulb, making it glow. It's this beautiful, simple chain reaction. Okay, get ready for something that's gonna kind of blow your mind. While each individual electron actually drifts along pretty slowly, the wave of energy they create, the actual electrical signal, travels at nearly the speed of light. That's why when you flip a switch, the light turns on instantly. The push is felt down the entire line of electrons almost at once. So, if you only remember one thing from all this, let it be this simple phrase. At its very core, electricity is the movement of electrons caused by voltage. That's it. It's that simple, and it's that profound.
It's amazing, really. This simple, organized flow of unimaginably tiny particles, it powers literally everything in our modern civilization. Your computer, your car, entire cities. So the question is, knowing how it works on this tiny, tiny level, what do you think it's going to power next?